Just before the midterm, we finished with this, how do we encode digital data, zeros and ones, as some digital signal, some pulses. And you had in the midterm exam a question about non-return to zero invert on ones. That was one example. And another question about Manchester encoding. So they were examples of, you've got bits, you need to send a digital signal. How do you encode those bits onto a signal? But of course we have other approaches depending upon whether we have analog or digital data or we want to transmit analog or digital signals. Today we'll look at the next two. Quickly go through the next one, which is if we have digital data but we want to transmit analog signals. We want to send some continuous waveform, but we still want to send bits. And then spend some more time on the third one. Digital data analog signals. Example, our telephone network, the fixed landline telephone network. So the telephone line from your home to a telephone exchange transmits or carries analog signals. But we want to sometimes send digital data across that. We want to send data across the internet. So we have our transmission system that carries analog signals, but we have digital data, so we need something to convert our data into an analog signal. Many or some wireless systems, microwave wireless systems, use this approach where they send some analog signal from some wireless transmitter to a wireless receiver and carries digital data. What type of signal do we create? Now, just as a reminder, and you all know this, what's our basic signal? Our sine wave. If I draw a sine wave, and we have an equation to represent this, S of t equals the amplitude sine 2 pi ft plus the phase. That's our generic signal equation. Of course, our signals are a combination of different sinusoid components, but that's the simplest form. We have a sine wave with some amplitude, some frequency, and some phase, where the phase is the shift from some origin. We want to have our input bits, zeros and ones, and generate a signal such that the receiver can, when it receives a signal, can interpret what bits were sent. And this process that we go through is we take our bits and we vary our signal. We vary one of these components, amplitude, frequency or phase, depending upon the bits that we want to send. The simplest example, I want to send a bit 0, use high amplitude. I want to send a bit 1, use a low amplitude. There's one example. Vary the amplitude depending upon the bits you want to send. So change the amplitude of your sine wave. This process of varying our analog signal is called modulation. It's the concept of varying our analog signal according to the data is modulation. So what the transmitter does is it takes the data and varies or generates an output analog signal which varies depending upon the input data. So it modulates the signal, and the receiver demodulates. The receiver takes an analog signal and gets the data back. So that's demodulation. So a device that can both transmit and receive, or modulate and demodulate, is called a modem, a modulator and demodulator. According to our equation, we've got three things that we can vary to change the shape of our signal: the amplitude, the frequency and the phase. And we did this in one of our first lectures. We saw the shape of our sine changes when we change these values. And we do the same here, is that by varying one of these, we can represent our bits, 0 and 1. By varying the amplitude, phase or frequency, we can have a signal that represents bit 0 or bit 1. And the process is called shift keying. So if we change the amplitude of our signal to represent the bits, it's called amplitude shift keying. If we change the frequency of our signal to represent the bits, frequency shift keying, and phase shift keying is the third approach. So what we do is we generate a signal like shown here, and depending upon the data that I want to send, I will either change the amplitude of this signal or the frequency of this signal or the phase of this signal. This input signal, or this original signal, is called our carrier signal. It carries the data. And the frequency of that is called the FC, or the frequency of the carrier frequency. We'll see an example in a moment. So what I do is I transmit a signal. If I'm using amplitude shift keying, the signal will have, say, some frequency, some sine wave. And if I transmit a bit 0, it will have one amplitude. If I transmit a bit 1, it will have a different amplitude. The three approaches of amplitude shift keying, frequency shift keying, and phase shift keying are shown in an example here. At the top is our original data for an example. This is just an example of our data, 0, 0, 1, 1, and so on. A sequence of data that I want to send. Below the data is a digital signal using what technique? What technique maps this data to this digital signal? Not of the ones we're talking about today, but from last. NRZL. There are two forms of NRZ, NRZ. Non-return to zero. The basic form is, just non-return to zero level, it's called. And the other one is invert on ones. In your exam, you had one on invert on ones, I think. But this is the simplest form. Bit 0, high, bit 1, low. That's from before. We don't need to worry about that digital signal for this example. Just focus on the data. And now let's look at if we use amplitude shift keying. What we do is that the transmitter has a scheme that says, if I want to transmit a bit 0, set the amplitude of my signal to some value. In this example, the value is 0, or an amplitude of 0. It doesn't have to be, that's common. Let's say set it to 0. If I want to send a bit 1, set the amplitude of my signal to some positive value. Let's say this is at +1. There's an example of amplitude shift keying. What the transmitter does is takes some signal at a particular frequency. When it needs to send a 0, it sets the amplitude of that signal to 0. And when it needs to send a 1, it sets the amplitude of that signal to 1. And just keeps changing for some duration of time. So for this duration, it transmits a signal with amplitude 0, and then 0, and here the amplitude of the signal is non-zero, 1 for example, and so on. The receiver receives a signal, measures the amplitude of that signal for that duration. If it's received to be 0 or close to 0, then it assumes the bit received is 0. If the received signal has an amplitude of 1 or close to 1, then it assumes the received bit is 1. So a very simple way to convert or transmit our bits as an analog signal. And the other two, frequency and phase shift keying, the same concept, except instead of changing the amplitude of the signal, change the frequency. We can see here we have one low frequency and here a higher frequency. And here change the phase. Remember, the phase is this offset or the shift of the signal, that sine wave. The normal, you think of a normal sine wave, you go up and then down and so on. With a different phase, you could be the opposite and initially go down and then up. That'll be a different phase. And that's what's used here. Bit 0, we have the opposite phase where we go down and then up. So we initially go down in our sine wave. Bit 1, the normal phase or a 0 phase, we go up and then down. So by changing the phase, we can represent the different bits of the data. So we could write that as an example. This is our ASK, FSK, frequency shift keying. let's say frequency to transmit bit 0, I use a frequency of, let's say, 1 Hertz. And to transmit a bit 1 in this case, I use a higher frequency. If this is 1 Hertz and this repeats 2 times in the same interval, that would be 2 Hertz. So an example for frequency shift keying, depending upon the bit, 0 or 1, we change the frequency of our signal. And for phase shift keying, in this case, with a bit 1, we just have the normal sine wave, that is a phase of 0. And a bit 0, we go down then up. I think that gives us a phase of, is it 180 degrees? These are just example values. Of course, they don't have to be these 2 values, the amplitude, the frequency, or the phase, just examples. They could be any values as long as they're different. And that's the idea. We can extend them. We don't have to use 2 levels. Here we have 2 amplitudes, 2 frequencies, or 2 phases. We can extend them to use more than 2 levels. We could have 4 different amplitudes, where each amplitude represents 2 bits of data. An example, let's say we have this scheme. We have 4 levels. Amplitude of, let's say, 0, 0.2, 0.6 and 1. Here's a different scheme, but using amplitude shift keying. The concept is that we use 4 levels in this case, where if I want to transmit the bits 0, 0, I transmit a signal with amplitude of 0. If I want to transmit the bits 1, 0, my signal has amplitude 0.6. I'll try and draw. It won't be very accurate. Let's try and draw that. The same sequence of bits. So now we operate on a pair of bits at a time. The first 2 bits are 0, 0. Therefore, I send my signal with amplitude of 0 for some period of time. Let's get a different colour. Zero amplitude, that's easy. The next 2 bits are 1, 1. So I transmit my signal with amplitude 1.0. Let's say this goes up to 1.0. The next 2 bits, 0, 1, transmit my signal with amplitude 0.2. So at this point, wherever, if this is 0.2, and so on. Okay, we change the amplitude according to the bits that we want to send. Here we have 4 levels, 2 bits per level. We can have more levels, 8, 16, and so on. And we can do the same with the other approaches. With frequencies, we could have 4 different frequencies, 4 different phases. So we can extend them to have an arbitrary number of levels. What's the advantage of having more levels? We've mentioned this before when we talked about how we encode bits onto our signal. More levels means not so much related. Maybe, but that's not the main point. What's a good thing about having more levels? Let's say if this period here, the duration for one signal element is the same as this period here, in the first approach where we have just 2 levels, every signal element, that is this duration, carries 1 bit of data. Here, this signal element carries 2 bits of data. This corresponds to 0, 0. From here to here is 1, 1, and then 0, 1. Every signal element here corresponds to 2 bits of data. In the slide, every signal element corresponds to just 1 bit of data. Given the same signalling rate, increasing the number of levels increases our data rate. We've seen that in some examples before the midterm. Increasing the number of levels increases the data rate that we can achieve. Because if I send my sine wave at the same rate, all I do is change the amplitude. So this, assuming if you match my diagram to the slide, this period is the same as this. So I'm sending more bits per signal element or per period here. And gives me higher data rate, with all other conditions the same. More levels, higher data rate. That's a good thing. What's the problem with more levels? Noise causes a problem. What's the problem? Errors. The receiver's job is, when it receives a signal, in the presence of noise, the received signal may not be exactly what was transmitted. So if what's received is not this perfectly, but what is received is this, then what the receiver does is looks at the received signal and matches it to the closest of what was transmitted. And the more levels we have here, the higher chance that the same amount of noise will cause an error. That is, that with a small amount of noise, it was transmitted at 0.2, but the receiver thinks it was, say, 0.6 that was transmitted. That would be an error. The more levels we have, the higher the chance of errors. More levels, higher data rate, but more errors. That's a trade-off that we need to consider. We can't just keep adding levels, 4, 16, 256, to 10 million levels, because the more levels, even though higher data rate, more errors. So, with digital data, we want to generate an analog signal by either changing the amplitude, frequency or phase. And we can have more than 2 levels. The B here refers to binary. Binary meaning 2 levels. It's common for especially frequency and phase shift keying to expand the number of levels to be more than 2. You'll see Q meaning quaternary or 4 levels, and others, 8 PSK or 8 FSK meaning 8 levels and so on. The other thing we can do is combine them. And a common combination is combine the amplitude shift keying and phase shift keying. That is, here I had 4 levels just by changing the amplitude. Another approach could be have 4 levels but change both the phase and the amplitude. Here's another scheme. How will I write it? If we want to transmit the bits 0, 0, send with amplitude equal to 1 and phase equal to, let's say, 45 degrees, just as a different example. It could be a different value. If I want to send 0, 1, send with amplitude of 2 and phase of 45 degrees. 1, 0, amplitude of 1 and phase of 135 degrees, a different phase. 1, 1, amplitude of 2, phase of 135 degrees. By changing both the amplitude and the phase with 2 different phases and 2 different amplitudes, we get 4 combinations. So think of 4 different signal elements. One has an amplitude of 1, say the low amplitude, and some offset of 45 degrees. Another has a higher amplitude with the same offset. And these two, low and high amplitude, but the different offset. Remember, the phase is some shift of the signal from some origin point. It's hard to visualize exactly what these look like. I will not try. So we can combine the amplitude and the phase shift keying, or in theory, any of the three can be combined. This is shifting the amplitude. This is shifting the phase. The common name for combining these two together, amplitude and phase shift keying, is called quadrature amplitude modulation, QAM. And some of them are described here. They're all used in practice, all the shift keying approaches, some in different areas than others. It turns out that amplitude shift keying is generally less efficient than the others in the use of bandwidth. So it's only used in cases where you need to send a small data rate or you have a lot of bandwidth. In some case, like optical fibre, there's a lot of bandwidth available, so efficiency is not so important. Frequency shift keying, for example, is used in some coaxial cable systems, in some radio wireless systems, and is often extended to not just 2 frequencies, but M frequencies. Not binary frequency shift keying, 2 levels, but 4 levels, 8 levels, 16 levels, and so on. Same with phase shift keying. It's extended with multiple phases, not just 2 phases, but M phases. Q, quaternary, means 4. So QPSK you may see sometimes means really PSK with 4 levels, but there are more. Used in many wireless systems. The special case of combining amplitude shift keying with phase shift keying is referred to as quadrature amplitude modulation, QAM. That's an example. ADSL, your home internet. Many wireless systems use QAM. Some examples. Actually, on the next slide, there are some examples. That's the main points that we want to describe about these shift keying approaches. The basics, 2 levels, shift either the amplitude, frequency, or phase. We can extend them to have multiple levels, and we can combine them to get multiple levels. They have their different advantages and disadvantages. The next 2 slides give just some different examples. We will not go through them. And final, some example uses. Optical fibre, what's RFID? Anyone? RFID is those small RF transmitters that may be embedded in like barcodes in devices, so you can track objects and so on. And that's an example of using amplitude shift keying. Frequency shift keying is used in, for example, UHF and VHF communications, walkie-talkie style communications. Phase shift keying and the combination with amplitude shift keying, QAM, used in many cases. Mobile phones, Wi-Fi, wireless LAN, cable modems, different DSL, ADSL technologies use QAM and others. And the number of levels that they use varies. Remember, the more levels, the higher the data rate, but the more errors. And generally, the more levels you have, the more complex the transmitter and receiver is. It's harder to build the device. What were some numbers? Some cable TV systems use 64 QAM. You don't have to remember this, just some examples, and 256 QAM. That is 256 levels, varying both the phase and the amplitude of the signal. So 256 combinations, 8 bits per signal element. VDSL2, VDSL is similar to ADSL, except it only works over short distances, maybe 10, 100 meters. You send data across a copper wire using VDSL. VDSL2 uses, what is it? Up to, it uses different levels, 32,000 QAM. 32,000 levels, 32,000 different combinations of phases and amplitudes to transmit the data. I.e., what's that? 16 bits per signal element. 16 bits can represent 32,000. Just some examples that these are commonly used in different wireless and wired transmission systems. Any questions on how shift keying works? Quite simple. We're not going to go through any more details. Answer the final exam question on shift keying, can you? Just understand that going back to our basic sine signal, 3 things we can change: amplitude, frequency and phase. By changing them, we can represent different bits. That's the easy one. Let's now move into how do we send our analog data. So this was about sending bits, digital data. Before the midterm was about sending bits, digital data as a digital signal. Now let's look, how do we send analog data? What's an example of analog data? Anyone? Analog data. Voice. Voice is a good example because we use it all the time. So analog data, remember, is continuously varying. It's not a discrete values. It's continuously varying over time. How do we send analog data? Well, we look at how do we send it by encoding into digital data. So specifically, we're looking at, we have some analog data like voice, some voice input, and we want to send it as digital signals. And we use a codec. But what's a codec do? Well, we'll see that we in fact convert the analog data into digital data. So in fact, there's 2 steps. Convert our analog data, like our voice, into bits. And then use one of these techniques to transmit it. Because once we have digital data, we can either use digital signals or analog signals. Manchester, non-return to 0, or any of the frequency, or any of the shift keying approaches. So in fact, what we cover here is how do we convert analog data to digital data. Once we have digital data, we can use one of our previous techniques to transmit it. So let's focus on that. We can either convert the analog data to digital and then transmit that as a digital signal, for example, using NRZ, or convert it to digital data and then modulate that and transmit it as an analog signal, like the previous examples of phase shift keying, frequency shift keying. The point here is that we convert the analog to digital data. And that's the process that we're going to focus on. And that involves using a codec. We want to digitize our analog data. We have some continuously varying input. We want to get bits as an output. And the name of the process of converting our analog data into digital data, we encode the digital data, or we code the analog as a digital data, and the opposite of converting that digital data back to analog, we decode. So together we get a codec, a coder or an encoder and a decoder. What's wrong with this statement? I think the last one's back to front. A codec converts analog to digital data from the transmitter. The receiver does the opposite, converts digital to analog. So this is wrong. It recovers the analog data from digital data. So just correct that in your notes. This should be analog, this should be digital. That is, we receive digital data and we get the original analog output. That is, recover the analog. there are different types of codecs, okay, and you've heard of some, like especially with audio codecs and even video codecs. A common one, or a basic one, is called pulse code modulation, and in this course we will cover that. The slides have another variation called delta modulation, and there are many others, okay? But to show the basics, we'll go through PCM, pulse code modulation. That's the general procedure for PCM. Here's an example of some analog data as input. Right, so sine wave, but it's analog data. That's our input. We want to get as an output digital data, zeros and ones. The process that we go through with PCM is that first, note that this is continuous in the time domain and it's continuous in the amplitude. That is, if you look in the time, as time increases, we have a continuous varying value, and the amplitude is continuously varying, going up and down. Digital data is discrete. We have discrete values, zeros or ones, for some particular time. We need to convert the continuously varying analog data into discrete digital data. And the process, as shown up here, is the first step is we have our input, which is continuous in time and amplitude. We take samples of the analog data. At different time points, remember time increases, we record the value. At this time, and sometime later, record the value, and these dots may not be to scale, but what we do is we take samples of the input analog by recording the value at different time points. Okay? Where, in fact, there's not much use of drawing this because you'll see it on the next slide. And it's better drawn. Normally, the time between samples is called the sampling period. So we record the value of the analog input at discrete time points. So it's no longer continuous. The input is continuously varying over time. By taking samples, we turn it into discrete variations over time. One point and then another and so on. So that's what our sampler does. It's called a PAM, or a pulse amplitude modulation sampler. What it does is takes a value at some sample point, or records the value of the analog at some sample point and returns some output value. Then the next step is that we turn, so as the output we have something which is discrete in time but continuous in amplitude. For example, the amplitude here may be 1.1036. Here it may be, 4.614. So continuous values. What we do is we map these continuous values of the amplitude into discrete values. And we can think of them, map them into different discrete levels or code numbers. And that's what the quantizer does. Instead of recording the value 1.1036, it maps it to one level. That is, we divide this space into multiple levels. For example, if we divide it into 1, 2, 3, 4 levels, this value maps to level 3. This value, level 4. This one, 1, 3, 4, 1, 2, 3, and so on, depending upon how we divide the space into levels. And the result is that we get discrete values of the amplitude. So we start with a signal or an input which is continuous in time and continuous in amplitude. We take samples, so we get discrete in time, but still continuous in amplitude. And then we quantize, which is we map the continuous amplitude values into discrete values, and then we get some number, say some decimal number, and we encode that as a digital value, as bits. This is best described with an example. It may seem complex, but you'll see with the example it's a rather simple process. What we have here is the solid line is our input analog data. There's some varying analog input. So what we do is at different time points, we record the value, the amplitude. We take samples of the data. And in this example, the sample points are here, 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 and so on. The vertical lines indicate the sample points for this example. So we have a sample period, the time between samples, TS, and similarly we have a sample rate or a sample frequency. What we do is we divide the magnitude into discrete levels. Here we've normalized it. Okay, the minimum magnitude can be 0, the maximum is 16 at the top. So just, okay, normalize the magnitude. At the first sampling point, we record the value of the input signal. At this time, the value we record, where are we? 1.1 here. So ignore the left-hand scale, look at this scale just for now. This is our magnitude of 0, up the top is a magnitude of 16. So at the first sample point, look at our magnitude, it's about 1.1. Okay? That's this value. At the next sample point, the value up here is 9.2, as we give here. So all we're doing is at each sample point record the magnitude. At this sample point, the value is 2 point something, 2.8, okay, here. These are the values of the amplitude at the different sample points. But we need to map them to discrete levels, also called code numbers. And in this example, we're mapping them to code numbers or levels from 0 to 15. We effectively divide this space into 16 different levels. And the closest one, the measured value is 2, becomes the code number or the level. So this one, the way to interpret this left scale is anything within this band corresponds to level 1. Anything below is level 0. 0, 1, 2, 3, and so on. Is that right? No. Anything within this band is 0, 1, 2, 3, 4, and up to 15 at the top. So what we get, focus on this first point. Absolute magnitude is 1.1. It's in this band here, that is, it's between 1 and 2, and therefore it's mapped to the level or code number 1. So anything between these two horizontal lines becomes the code number 1. Between these two is 0, and so on. So the measured value of 1.1 becomes the code number or the level 1. Let's focus on one at the end. Here the measured value is 2.7. It's between 2 and 3. Anything between 2 and 3 becomes code number 2. 2.7, becomes code number 2. So we just map the values, the normalized magnitudes, to one of the, in this case, 16 different levels, from 0 to 15. Then we convert those code numbers to bits, which is called the PCM code. We convert the decimal value 1 to the binary 001, 0001. Why 4 bits? Why 4 bits? No. Why 4 bits? Why didn't I just write 0, 1 or just simply 1 in binary? Why did I write 4 bits here? It's binary. Why 4-bit binary? Why not 2-bit? Why not 8-bit? Why not 100-bit binary? Again, and more specifically, why 4 bits? Because there are 16 code numbers, or 16 different levels. So there are 16 possible values that I can get as an output. To represent 16 different values, that is 0 to 15, I need a 4-bit value. With 4 bits, I can represent 0 up to 15. So here I have 16 different code numbers, or 16 different levels. So I need a 4-bit number to represent those uniquely. So that's why I have 4 bits here, because I have 16 levels here. Similar. At the second point, that normalized magnitude we look here is 9.2. It maps to level 9. That is, it's between 9 and 10. So in this example, it maps to level 9, or code number 9. Code number 9 in binary, 4-bit binary, is 1001. And so on for the rest. Here's our input analog data. Here is our output digital data. So this is the output. This sequence of, what have we got, 28 bits represents this analog data. We've performed our pulse code modulation. Now, if we want to send that across the network, we send the bits across the network using frequency shift keying, Manchester encoding, or some other approach. Let's go through a more detailed example. Same approach. We'll see the concepts come up again. And then we'll answer some questions about the best way to do this. The example you have in your lecture notes or in your printouts, it's at the end of the current set of lecture notes. So you have this example. Just a different input analog data, and we'll go through different cases of using PCM to encode it. Here's our input, just some analog data. I want to convert that to bits and send those bits across a link. And I'm going to use PCM to encode that analog into digital data. So I've added some timescale here. So we say the analog input ranges from 0 to 18 milliseconds, just for an example, and some amplitude. I'm going to go through 3 different cases of how we use PCM. The first case, we're using a sampling interval of 4 milliseconds. That means every 4 milliseconds, I'll take a sample of my input analog data. Four-millisecond sample interval, and we will use 8 different levels. And I've drawn that on this diagram where 8 different levels from 0 up to 7. Anything within this band corresponds to level 0. Any value in here, level 1, level 2, up to level 7. So quite simply, when we sample a value, we will see whether it's within this band. If it is, then the code number will be 0. Okay? And we'll do it every 4 milliseconds. What's the first value in binary? In binary, what's the first value?
0, 0.
Why 3 bits?
There are 8.
All right, so we're going to...
8 levels.
There are 8 levels. So the one thing you know that with 8 levels, we need 3 bits to represent those values. 0, 0, 0 up to 1, 1, 1, 0 up to 7 in decimal. So every sample is going to produce a 3-bit value. The first sample at time 0, here, the magnitude is what? Well, the magnitude doesn't matter what the value is. The magnitude is in this band. It maps to level 1, or code number 1 in this case. Anything within here becomes 1. In decimal, 1. In binary, the 3-bit value is 0, 0, 1. Here's our output digital data for the first sample. Next sample. Because we're sampling every 4 milliseconds, now at time 4, record the value, and it's here, it's within the range for level 6. Okay? So it's just above this cutoff here. 6 becomes 110. Successful? Okay, good. And so on. Every 4 milliseconds in this example, 0, 4, 8, 12, 16, record the value, map it to one of the levels or one of the code numbers where this diagram shows those levels on the vertical axis. So we get this sequence of digital data. And we transmit those bits. So I want to send this analog data across a link or a network. Let's say that this is someone using their mobile phone. It's a very simple example, but let's say the input is you talking. You're talking on your mobile phone. You create analog input to your microphone on the phone. The phone has a codec. And what the codec does is the procedure we've gone through, take samples of your analog input and map it to bits. And then your mobile phone has those bits and transmits those bits across the air to eventually to the receiver. So in our case 1, how many bits per second do we need to send? Or easier, how many bits per second do we generate at the transmitter? It's our input analog data. We're generating these bits. We're generating 3 bits every 4 milliseconds. 3 bits every 4 milliseconds are generated at your transmitter mobile phone. You transmit 3 bits every 4 milliseconds to the receiver. The receiver takes those 3 bits every 4 milliseconds and produces on the speaker some analog output, which should be close to your voice. That's the idea. So for this to work, we need to send 3 bits per 4 milliseconds. Turns out to be 750 bits per second. Okay. 3 bits every 4 milliseconds is, because we have 250 samples per second, is 750 bits per second. That's how fast we need to send to transmit this analog data from A to B. Yes. Here. There's 1 sample every 4 milliseconds, 250 samples every 1 second. Every sample is 3 bits, so 250 samples in 1 second, 3 bits per sample is 750 bits per second. So it's simply the number of bits per sample times by the number of samples per second, or divided by the sample period. Three bits per 4 milliseconds is the same as 750 bits per second. That's the data rate I require to send my analog data to the receiver. It looks like the top diagram. Here you are talking on your mobile phone. You're generating the blue input data. The microphone on your phone takes that analog data as input, and the codec in the phone converts it to bits, okay, like we just did. And then your phone transmits those bits across the network. Eventually those bits are received by your friend's phone. Your friend's phone uses the decoder. It takes those bits and generates on the speaker on the friend's phone some analog output, which may look like this. You would like the output data to look the same as the input data. So it sounds the same, for example, with audio. Let's look at how this output data is generated. This is the output at the receiver. This was what we generated at the transmitter. Go back. Input at the transmitter. We generate these bits from that input. We send those bits to the other side. Therefore, the other side receives this sequence of bits. This sequence down the bottom. And it knows every 4 milliseconds I need to play back some audio. So, at time 0, between 0 and 4, it generates some output level, some analog output at level 1. 1 because we have the bits 001. Level 1. From 4 to 8, the next period, we received decimal 6. I can convert, this is 110, decimal 6. So we output at level 6. The next bits received 011, level 3, level 1, level 2. So what your receiver's mobile phone does is generate some analog output at some level for a period of time, the sample period. And you hear a noise which corresponds to the variations of the audio according to this. Is the received data the same as the transmitted data? No. Blue one is what we start with, the input data. The green one is what we receive. They are different. Because we've applied this process of digitizing the analog, we don't get an exact replication of the original input. We get an approximation. You can see this, the shape is similar. It's not always close, but we can see that, okay, the input is low, our output is low. Then there's this sort of quick increase on the input, so we get this jump in the output. And then we've got this decrease, so this reduction in the output, and then a slower decrease, and then it slightly goes up. So, of course, they're not the same, but the output has a similar shape to the input. We would like it to be as close as possible. Why? Accuracy. Again, the blue one, imagine, is your voice. You're talking. The green one is the audio output at your friend's phone. For them to understand you, then the output on the speaker at your friend's phone needs to reproduce your voice that you started with. Now, with audio, it doesn't have to be an exact, perfect replication of the input. Because your ears, you can distinguish what someone's saying, even if it's not exactly the same variations in the amplitude and the same frequencies of the audio. So, as long as it's close to what the input is with a phone, with audio, you'll still be able to understand what that person's saying. The closer it is, the more accurate or the higher the quality the output will be. The less accurate it is, the lower the quality, the worse it sounds. That's with audio as an example. How do we make it more accurate? How do we make the green one closer to the blue one? More samples. More samples. In the example, we sampled every 4 milliseconds. So you see with the green one, we only get a change in the level every 4 milliseconds at the output. If we sampled more often, every 2 milliseconds or every 1 millisecond, the output would change on a more regular basis and it will start to be closer to the blue one. Increasing the sampling rate or reducing the sample period will increase the accuracy. What else? Amplifier will not help. You just amplified a bad signal. What else? More samples? Yes. What else? How do I make the green one close to the blue one? Yes, sample more often. And what's my other parameter? And what do you do with the levels? Increase the number of levels. Note the green one, the values at the output can either be 0, 1 or up to 7. 8 different values at the output. If I had 16, there would be 16 possible values. We could get closer to the input. If I had 1,000 possible values as output, 1,000 different levels, we could get even closer and closer. Increase the number of levels, reduce the sample period, will give you more accuracy at the receiver. Let's go through 2 more cases to try and illustrate that. Case 2, same input, but we have a 2 millisecond sample interval, still 8 levels. And you can go through the steps. So instead of every 4 milliseconds, every 2 milliseconds record the value and map it to a level. 1, 3, 0, 1, 1. At 4 is still 6. At times 6, also 6, and so on. So we have more samples. Okay? Sample more often. Here's the output. And here's the original input. It's a little bit closer than the other one, and we'll show it again later to compare all 3 cases. In same number of levels, decrease the sample period, and we get the green one here. I'll compare all 3 cases in a moment. Case 3. Still 2 millisecond sample interval, but increased up to 16 levels. So every 2 milliseconds record a value, but it maps to a value between 0 and 15. Instead of between 0 and 7, we have more levels. That is, we have a finer grained representation of the analog input. And importantly, with 16 levels, we now need 4 bits per sample. This maps to level 2. In binary, 0010. 4 bits now instead of 3, because we need to represent any of 16 values. We need 4 bits. That's the output compared to the input. And now maybe clearer, a little bit clearer. Here's the 3 cases. The blue one is the input. We want our output to be as close as possible. Which one is the worst of those 3 cases? If you look at this plot, which one is worse? 1, why? Well, we see here the red one is 1. We cannot see all of it. Here's the blue one. Which one's closest? Well, we see here the red one, case 1, is a long way away from what it should be. Here, if you do not see red, it's because it's underneath one of these lines. That's all. Here, red is further away than the actual value than the green and the orange or the other colour one. So case 1 is the worst in this case. that's what we'd expect. It has the highest sample period and the lowest number of levels. The more number of levels, 8 to 16, and the lower the sampling period, 4 to 2, the more accurate we get. So the least accurate is case 1 in this case. As the, doesn't represent the input as close as the others. Case 2 and 3 are closer, we can see. In this example, it's maybe not the best example, it's not easy to see whether case 2 is or 3 is better. Anyone want to guess? Which one's better, 2 or 3 from this diagram? Well, maybe 3 is better because we see, say at this point, so they're the same in many cases. At this point, it seems to be a bit closer than case 2. 2 and 3 in this case are quite similar. They're better than 1, getting more accurate. In theory, case 3 is the best because it has the most number of levels and the smallest sampling period. We'll get more accurate with that case. If you increase the number of levels to 32 and you decrease the sampling period to 1 millisecond, you'll get even more accurate. You'll get closer to the blue line. Increase the number of levels to 32,000. Increase the sampling period, or decrease the sample period down to 0.1 milliseconds. It will be almost the same as the blue line. You get more accurate and accurate. So the trade-offs that we have here. The accuracy of the reproduced data at the receiver, that's what we care about. How accurate it is compared to the input. This is the sample period. The other way we measure it is the sample rate or frequency. The inverse. If we have a sample period of 4 milliseconds, the sample rate is 250 hertz. That is, every 4 milliseconds is the same as 250 times per second. So the sample frequency or sample rate of case 1 is 250 hertz. Here it will be 500 hertz and 500 hertz. This slide, the points it makes here, refers to the sampling rate or frequency. Increasing the sampling rate or frequency increases the accuracy. Increasing the number of levels increases the accuracy. Increasing levels, more accurate. Increasing the sample rate or frequency, more accurate. And of course, the opposite, less accurate if you decrease them. As a result, 3 is more accurate than 1 in our example. Go back to case 2. How many bits per second? In case 2. We're almost finished. Okay. How many bits per second are we sending in case 2? Maybe easier. How many bits are we sending every 2 milliseconds here? 3 bits, so every sample consists of 3 bits. We sample every 2 milliseconds, so we're sending 3 bits every 2 milliseconds. 3 bits every 2 milliseconds. We have 500 samples per second, so 1,500 bits per second. In case 2, we need to send at 1,500 bits per second. And you can do the same for case 3. Here we have 4 bits every 2 milliseconds. 500 samples per second. 4 bits per sample is 2,000 bits per second. It's simply the sample size, number of bits, by the sample rate. For example, here we have 4 bits, the sample size, and the sample rate is 500 hertz, 500 times per second. 500 times 4 is 2,000 bits per second. Comparing 1, 2 and 3, which one's better from that perspective? All right, hands up. Let's ignore 2 because that's in the middle. Comparing 1 and 3, looking at the rate at which we need to send the data, which one is better? Case 1 or case 3? Hands up for case 1. Hands up for case 3. Case 3 is wrong. This is the amount of data we need to send to get the analog data to the other side. Okay? This one's better because to get the same analog data, remember all the analog data is the same. To get the analog data for the same period of time to the other side, here we need to send 750 bits per second. In case 3, we need to send 2,000 bits per second. We need to send more bits to get the same data to the other side. We think we're less efficient in this case. We're sending analog data from one A to B. Here we need to send it 750 bits per second, case 3, 2,000 bits per second. So case 1 is better. Another way to think of it is that your link has a capacity of 1,000 bits per second. If the link has a capacity of 1,000 bits per second, we can send the data using case 1 because it only requires 750. But we could not send the data across that 1,000 bit per second if we use the approach in case 2 or 3 because they require 1,500 or 2,000. So this is not the capacity. The lower the value, the better. It's what's required to be sent to deliver the data. So we want to send our analog data with as few bits as possible. We want to send this blue line, the analog data for 18 milliseconds, using as few bits as possible so that we have space to send other information through on there. So case 1 is better from that perspective. And that's summarised. In terms of accuracy, case 3 is better. Or increasing the sampling rate or increasing the levels increases accuracy. But the trade-off is increasing the sampling rate and increasing the levels increases the data rate required. Note, required. That's bad. So we need more data rate if we increase these values. We want to use as few bits as possible. So high sampling rate, high number of levels, good for accuracy, but bad in terms of consuming our data rate. So there's no one answer as to which one is best. We need to trade off those values. Choose a sampling rate and the number of levels that gives good enough accuracy, but low enough bits per second. Yep. So now we compare to case 1, 2 and 3, which one's best? I cannot say because we know case 3 is more accurate, but it needs more data rate. So more accurate is good, more data rate is bad. Case 1, less accurate, but needs less data rate. So it depends upon your requirements. Yes, more data is bad because it uses more of our capacity. Let's finish with this example. I have a link from A to B. The capacity of that link is 1,000 bits per second. I want to send my analog data from A to B. I can choose between 3 different PCM schemes, 1, 2 and 3. Which one do I choose? Only case 1 will work, because case 1 requires me to send 750 bits per second. My capacity is 1000. Only case 1 will work. Case 2 and 3, the data rate required is too high, so no good in that case. Similar, if the capacity was another way to look at it, let's say 2,500. That's my capacity. And the analog data represents people talking. How many people can I allow to talk across my link if I use case 1? How many people at the same time can send their voice across the link using case 1? Case 1 uses 750, so with 3 people, we get 2250 bits per second. If there are 3 people communicating at the same time, each one sending 750 bits per second, then the total is 2,250 bits per second. My capacity is 2,500. With case 1, I can support 3 people communicating at the same time. What if I use case 2? How many people?
1.
With case 2, I can only support 1, because with case 2, I require 2,000 bits per second. I have a capacity of 2,500. So with case 2, I can only support 1 person talking at the same time. Case 3, how many people? What's case 3? 1 as well. 2,000 and 1,500. So again, case 1 is better from the perspective is that we can, with some given capacity, we only use a smaller amount of that. Therefore, we have more capacity spare for other uses. What we'll do tomorrow is look at some relationship between the sampling period and the signal, particularly the frequencies. So, in summary, PCM, we have analog data. We take samples at some sample rate. Those samples map to code levels, or code numbers, or simply levels. And those levels or code numbers are represented as bits, as digital data, and that's what's transmitted across our link. So we're mapping analog data into digital data, and then we can transmit that digital data. The more samples we have, the more levels we have, the better our signal at the receiver is reproduced, the more accurate it is. That's good. But the more samples we have and the more levels, the more data rate required. That's bad. So that's where the trade-off comes in. Tomorrow we'll continue and finish with some theoretical discussion and then move on to the next approach. Out of time for today.